is limited to object diagrams of bill of material problems because of the special error checking built into the compiler. The compiler has served two purposes. It solved the immediate problems of the target applications, and it was an important milestone in our continuing work on automating the OMT methodology. So, object diagram compiler illustrates several concepts such as the compiler architecture consists of four passes that step through a series of internal models. There are many relationships and functional dependencies within a model, but few between models. So the generic electric has several internal application. This is example. General electric is example. There are several internal applications that configure product assemblies. The business practice for these applications, the customer specifies the product function, the manufacturer must devise the corresponding product. For example, a customer might order a lawn mower that is a lightweight, inexpensive, and energy efficient. The manufacturer may fill the order with a mower that has a 1 horsepower, that is HP, gasoline powered engine, 45 centimeter diameter aluminum deck, and non mulching blade. These are the requirements for production of the lawn mower. This is the customers required only that the lawn mower that is lightweight, inexpensive, and energy efficient. This is the expectations of customer, and these requirements of customers given to the manufacturer. So manufacturer manufactures as per requirement. Maximum horsepower is 1, then it is gasoline powered engine, and which has a diameter 45 centimeter of aluminum deck and non mulching blade. So General Electric does not manufacture lawnmowers. We use lawnmower example for convenience. Similarly, the list of parts selected by manufacturer to build a product called as a bill of material, that is BOM. A BOM or bill of material is a tree of direct and indirect parts of compose and assembly. The literature often refers to a bill of material as a part explosion problems. Bill of material are often printed out as intended parts list where the indentation corresponds to the depth in the hierarchy. So this is the example. This figure shows the bill of material of lawnmower. The first value listed after each part. This is the first value listed after each part is a part number. Here lawnmower LM number is 16G. So thus lawnmower LM16G is engine E1, which have engine E1, then deck D16, and so forth. So first value engine E1, piston P1, then wires W15, blade B16. This first value or first part of number after each part is part number. This is part number E1, P1, D16, B16, WH3. These are the part numbers and part properties follow the part numbers. Suppose this engine E1, this is part number and part property is 1 HP gas powered. Piston P1 and P1 has properties 5 centimeter long, 5 centimeter, 0.5 centimeter diameter. Then carburetor car B9, then wires W15 which have properties quantity 4, oil resistance and so many. This is one sample example of engine. So this chapter or this part describes the portion of new bill of material configuration system, a subsystem called the object diagram compiler. First, we draw an object diagram of bill of material parts explosion with an ordinary graphics editor by carefully placing many lines, triangles, boxes, test strings, and other primitives. The object diagram compiler then processes an object diagram and ultimately generates database DBMS commands and that create tables and indexes. Whenever we change the object diagram, we return the compiler and generates a new DBMS commands. Thus, the object diagram is a living document. Thus, the object diagram is a living document. The object diagram compiler simplifies documentation and DBMS schema generates by using the same source document for both. Our success with the object diagram compiler has motivated further work towards developing more comprehensive tools for automating the OMT methodology. This is the background of object diagram compiler. Then what is a problem statement? Whenever you should do a project, any project have its background, then there is a problem statement, and every problem statement must consist of input, output, and basic requirements regarding that projects. See here figure shows the objective of the object diagram compiler is translate bill of material object diagrams into database commands and checks the input errors. So bill of left side, the bill of material object diagram drawn with graphics editor, then transferred to graphics editor statements, then transferred to the compiler. So error message sends to one side and remaining database commands sends towards data dictionary. This is the problem statement regarding bill of material. So for any project you should have a problem statement and each problem statement have input, have output and basic requirement. So we will study the compiler input, compiler output and miscellaneous requirements in detail. So this is the compiler input. We have seen the example as lawnmower in case of engine. So each mower have its own number and its own width. Then it has the properties like blades and engine, and each Blade have blade number, blade length, and mulching. Similarly, in case of engine, engine number, motive power, and horsepower. So the compiler must read an ASCII description of bill of material object diagram produced by general purpose graphics editor. We used a framework, but others such as Macdraw or Interleaf are also suitable. The graphics editor must be geometric shaped and not pixel based. The compiler input is analogous to the source code of the conventional programming language compiler. So figure shows the bill of material object diagram of lawnmower has blade and engine. Each blade has alignment left, right, justified center. So lawnmower has blade and engine. Each blade and engine may be associated with several lawnmower. So the object diagram. This is the object diagram. Object diagram compiler must support basic object modeling, constructs, classes, attributes, binary associations, binary aggregations, and generalizations. The compiler does not need to support object modeling constructs that are not needed for our bill of material applications, such as qualified associations, n-array, relationships, and operations. So we'll see for generating any graphics, we have we should know the different shapes. So first shape we have taken is a rectangle, then rectangle class rectangle, then b rect. These are the properties: 3.06 inch, then 5.65 inch, then 1.06 inch, and 0.28 inch. These are the properties regarding the rectangle class and end of the rectangle. Similarly, for the class text line, TL, TL for text line. So text line it have origin 0.58 inch, then 5.83 inch. Then each text line have alignment left, right, justified, center. So here we have taken alignment as a center. Then font, text line of font should be bold. Then end of font. Then string, regarding string is suppose blade. Then end of text line. Then we have taken next class as again rectangle, which have different properties: 3.06 as it is previous, 5.93 new, 1.06 as again previous, then 0.49 is new, then end of rectangle class. Again next is text line, then new text line. So text line origin 3.14 inch, then 6.08 inch. Then now text line alignment now we have taken is left. For this text line we have taken alignment is left. Then font is F pen, then end of font. Then string is blade number. Previous string is blade. Now this string is blade number, and end of text line. Again we have taken next text line, text line origin 3.14, then 6.12, These are the x-axis and y-axis. So then text line alignment is left, string is blade length. Then end of text line. Again we have new text line origin 3.14, 6.36. Then again text line alignment left and string is mulching. So in case of blade, we have taken text line blade, blade number, then blade length and mulching. Then what is these are the inputs regarding the compiler input. Then what is the compiler output? Whenever you are given some input, there must be output. The compiler must produce a series of database commands. This output is executed as a script file to load a data dictionary. We use the Oracle DBMS, but any relational DBMS that support the SQL is suitable. The compiler must generate association names and determines how to implement relationships. The compiler output is analogous to the object code of the conventional programming language compiler. The object diagram compiler stores its output in data dictionary, custom designed for bill of material applications. So we used several downstream programs complete the process of creating the tables and indexes stored individual bill of material. We discussed this custom dictionary rather than the DBMS dictionary because we require bill of material specific extensions. Then what is basic requirement regarding these the problem statement? The object diagram compiler was subject to further requirements on development time and performance. The compiler had to be developed quickly in 4 months or less. It was the part of larger bill of material generation project and we didn't want to divert our attention. Our requirement on the execution time were more lax. An execution time of 2 hours or less is adequate because the compiler is a batch program that is only run at a system setup time. The compiler is not used the compiler is not used for day to day generation as a bill of material. As it turned out, because of skillful software engineering, performance was much better than required. So compiler must detect input errors but need not correct the errors. Whenever you should have to return any program in any language, compiler must detect input errors, but need not correct the errors. For example, class name must be unique, has less than 31 characters, and begin with alphabet characters. So compiler must not abort when it encounters user errors. The compiler must accept bad input. The compiler must accept bad input and keep running so that user can detect multiple errors from the single run. The compiler must tolerate imperfect connections since The object diagram are prepared with general purpose graphics editor. It is difficult to align and precisely connect everything. The compiler must accept input that looks correct when printed on paper. Also, the compiler must detect mistakes and that are not visible, such as superimposed drawing components. The compiler must isolate dependencies on graphic editors and relational DBMS within one or two modules. Then the compiler can be ported without major rewriting. Then third part is analysis. Whenever you have given input, your expected output and coming output, you should have to analyze. So analysis is the first step towards solving the problem statement. It quickly becomes apparent that the difference in the level of abstraction between input and output was too great to span in a single step. We decided that it would be the best to use several passes. This conclusion is not surprising since many compilers requires multiple passes. And what is the disadvantage of multiple pass? The disadvantage of multiple pass approach is that the developer must prepare multiple object modules and design multiple compilation phases. Advantage of multiple passes is the complexity is addressed in divide and conquer fashion. The resulting code is easier to port since graphics editor and DBMS dependencies are isolated in small portions. So in this figure, this is functional model of object diagram compiler. Whenever you have given input, so there must be required or expected or unexpected output. So input ASCII description of object diagram. So whenever input is given, then password towards parse graphics editor language, then forwarded towards geometry model. So then there is exact connectivity. For connectivity, there is a connection forwarded towards connection model, then abstract bomb entity. Then there is internal meta model and generate database commands. And these are the expected or unexpected output. Whenever there is there are accurate input, there is accurate output. There are errors, it gives unexpected output. So output command to the load database or data dictionary. So so there are 7 parts in this figure. Also there are 7 parts. First, parse graphic editor language, parse graphics editor language, then geometry model, geometry object model, then extract connectivity, connection model or connection object model, abstract bomb entities, internal meta model or internal meta object model, and then generate database comments. These 7 parts from input to output will study one by one. So first, parse graphics editor language. The first pass reads The raw diagram FrameMaker file generated by graphics editor and builds geometry model. The first pass corresponds to the lexical analysis in a conventional programming language compiler. This pass requires little analysis effort beyond figuring out the correct BNF binary normal form syntax for graphics editor language. Our development of BNF grammar for the graphics editor was aided by vendor documentation. Then second is a geometry object model. So in this figure there is a geometry object model page and each page have page number. So this page have different shapes such as ellipse, rectangle, polyline, polygon, text line. These page numbers in different forms ellipse, rectangle, polyline, polygon and text line. So in case of ellipse or rectangle, in these two shapes have specific boundary, top location, bottom location, left location, then right location, height, width, whatever. These two shapes, ellipse or rectangle, these two shapes have boundary. Then polyline, polygon, text line have point. These are the polylines, polygons or text line have starting point and ending point. So and each point have x coordinator and y coordinator. So whenever any line or any polygon or any text line starts, and text line also contains alignment left, right, justified and centered. So polyline, polygon or text line each have starting point and which that point have x coordinator and y coordinator. Similarly for text line also a font. Text line may consist font size, italic, bold, regular, underline, whatever. These are the basic requirements of geometry object model. So graphics editor that we used organize the components by page. So each font describes then geometry model includes page number for use in error message. So ellipse, rectangle, polyline and polygon capture graphical information in the object diagram. Ellipses have location and a bounding rectangle. An ellipse may have hollow fill or solid fill. Rectangle have location, width and height. Polylines and polygons are composed of straight line segments that connect a sequence of points. A polyline is an arbitrary sequence of lines. A polygon is closed geometric figure. Then geometric module for our example, lawnmower example contains of the objects 6 rectangles, 11 text lines, 2 polygons, that is 2 diamonds, 2 ellipse, 2 polylines. Then third is extract connectivity. The second pass consolidates raw geometry, classifies size and shape and detects intersections. and the attachment of geometrical primitives. We call the output from the second pass the connection model. The figure in the next slide represents part of data flow diagram for this pass. Ellipses, rectangles, polygons, and text lines from the geometry models are input data stores in the functional models. Every class and association in the connection model is the output of one or more functional model processes. Recall that during analysis we do not specify algorithm but specify effects of the processes. In this figure, it is groups of continuous rectangles are recognized as blocks. Continuous rectangles are recognized as blocks such as text line. Then each block and net intersection is found is stored as a node. Ellipses are classified into multiplicity balls. These are the multiplicity balls, and each multiplicity ball is associated with node, and each reference is associated with a block, and each text line is bound to the nearest block or net. This is the extract connectivity. Then connection object model. The connection object model, the bridges, the geometry model, internal meta model. Classes that are shaded are carried forward from the geometry model, connection model towards an object model as a topology, a collection of blocks connected with nets. Blocks and nets have attached geometry and text. Here the example is given as a page number, and this is the page number. This page may be triangle, may be a diamond, and this page have a ball. Then page have page number that must be a reference, and a reference in the form of block, block name, or text line. These are associated with each others. See figure in detail. Each page have a node and associated with point axis and y axis locations. The block, net, and node classes form the core of the connectivity model. Each block has a name. A node corresponds to the exactly one block and one net. Each block may have many rules. Each net may have many nodes. A node may be connected to one ball or a diamond. A net may be connected to a triangle. A block may have several cross-reference circles pointing to other pages. Both blocks and nets have text. So the connection for our lawnmower example, three blocks named lawnmower blade engine, two nets named lawnmower blade, lawnmower engine, four nodes. two diamonds each associated with node, two solid balls associated with node. Lawnmower block is associated to text line as more number and more width. Similarly, association with our blade and engine. Then abstract bomb entities. The third pass arises the level of abstraction. The graphical symbols in a bill of material diagram have more meaning than their mere shape. A block denotes a class. A net represents a generalization or association. Pointer represents class and classifies relation applies hard coded rules for mapping relationships to tables. The second and third process correspond to the semantic analysis in a conventional programming language compiler. The functional model for this pass is complicated by extensive error checking. Much of this error checking derives from using general purpose graphics editor to construct the input object diagrams. The general In general, the user can make many diagram errors such as dangling association lines, duplicate class names, and class box without a name. The object diagram compiler also checks for errors peculiar to the bill of material generation. The pass-3 functional model is too large and complex to display here. Then internal meta-object model. So figure summarize the internal meta-object model that captures the meaning of bill of material. A bill of material database has many class and association tables. Each class table has many attributes. An attribute may be a role or non-role attribute. Non-role attributes belong to exactly one class or association table. Role attributes appear in many class and association tables. Role attributes connect together in various tables. A class associates with all blocks that refer to it. Each relationship associates one net. See here example block. Each block have block name associated with class table. Class table has class name, primary key name. So it have a role attribute. Similarly, class table is also non-role attribute. So attribute each attribute have attribute name and then attribute may have role or non-role. So it is again divided into two types role attribute and non-role attributes and they are and each attribute have superclass and subclass. In case of inheritance, similarly there is association table which have association name is associated with relationship with net and role attributes, non-role attributes. So this is the internal meta object model. So one object or attribute related with many models or many attributes. So bill of material database has many relationships. Each relationship is either a generalization or association. Association may be further refined into aggregation, and each generalization has one role attribute that denotes the superclass and many role attributes that denote the subclass. A discriminator indicates which subclass pertains the each superclass instance. Since the bill of material generation only uses binary associations and each association has exactly two role attributes. So an association may have zero or more non-role attributes. So the internal meta model for our lawnmower example is there are three class tables known as lawnmower blade engine. There is no association table, that is zero association table. Three role attributes: mower number, blade number, engine number. Five role attributes, non-role attributes. Two aggregation, both association and aggregation, and zero generalization, zero link values. Then seventh is generate database commands. The fourth and final pass transports the internal meta models into the database meta model. This process is simple because the internal meta model is similar to the database meta model. The last pass is analogous to the code generation in a conventional programming language compiler and produces the desired output of DBMS command. Then next part, after analysis, there is a system design. First, you have selected background of that project, then problem statement, then we have done analysis, then system design. Once analysis is done, the choice of system architecture for the object diagram compiler was straightforward and directly follows the overall functional model. We select to implement the program as batch transformation. The object diagram compiler consists of a sequence passes that transform between layers. We select a closed architecture where each layer can only access the object in itself and the immediate preceding layer. The advantage of closed architecture is increased information hiding, which simplifies debugging, extension, and porting. So the disadvantage of closed architecture relative to open is loss efficiency. The object diagram compiler efficiency is good because the careful design models, and this shows the linkage between object models as shaded. Thus, class table in internal meta model refers to the block into the model. The object diagram compiler completes the complete in full before preceding it. The use of there is a little locality reference of in our bill of material. So object diagram compiler manages all data in memory. So input is a file and output also is a file. There is no need to make immediate data visible outside the program. Since the program has a closed architecture, we consider the deallocating objects from earlier passes that are no longer needed to recover memory space. We didn't deallocate object because of extra logic required. and fear of dangling pointer bugs. Memory consumption has not caused us any problem to date. Implementation of control is not an issue. The object diagram compiler is a bottom program. The user has no interaction with the program after starting it. There is no interactive debugger. All error messages are printed to a file. Once again, our approach was dictated by simplicity. It was simpler not to provide an interactive debugger. The batch approach has worked well in practice. Then next is whenever there is a analysis, after analysis there is construction, then there is object designing. Most of work remaining after analysis was to implement association, prepare a pseudocode and write actual code. The process of writing pseudocode uncovered several analyses. We revised analysis as needed. The design was a straightforward application of object-oriented programming and mostly a matter of adding detail. So it have three parts: functional models, intermediate object models, and connectivity algorithms. We'll see in detail one by one. So first is functional model. In this problem, as in in many batch transformations, functional dependencies can be expressed as an acyclic directed graph among data stores containing sets of objects. Each data stores contains all objects of given class, such as rectangles and nodes, or all the links of a given association, such as ball node pairs. The data flow diagram can be constructed by examining each class and association in the output model and determining the input classes and associations that it depends on. In many cases, the final algorithm can be written down directly without actually drawing data flow diagram. We found that a marking approach a marking approach aids formulation of functional algorithms. A mark represents a class, association, or attribute that has been computed at a given point in the algorithm. First, all input classes and associations are marked on object diagram. Then all classes and associations in subsequent stage of the batch transformation are examined. The pseudocode for each attribute and association is written in terms of previously marked classes and associations, and the corresponding output attributes or association is marked. When all the attributes of the class are marked, then the entire class is marked. The entire output object The entire output object model is marked. The functional algorithm is complete. This marking technique works because the dependencies form a particular order. Blocks can be computed from rectangles, balls can be computed from ellipse, nets can be computed from polylines, nodes can be computed from nets and blocks. After this computation, ball node pair can be computed from ball and nodes. We didn't actually draw the data flow diagram because the functional algorithm is so directly derivable from the object model. The first pass reads a ASCII file that contains bill of material diagram and loads the geometry model. We use a Unix compiler generation tools for this pass to improve our productivity. This pass required a little design effort and no pseudo code. The second pass scans a geometry model and produces the connection model. The most of our design effort for this pass was concerned with devising graph traversal algorithm. The third pass, that is abstract bomb entities, scans the connection model and generates internal meta model. Like the second pass, most of the design effort for this pass concerned choice of algorithms. The fourth pass, that is generate database commands, scans the internal meta model and write DBMS commands to a file. All generalizations are implemented with distinct superclass and subclass tables. Some associations are represented by distinct tables, other are captured through buried foreign keys. Hard-coded rules in the object diagram compiler determine how to implement each association. Then second is intermediate object code or intermediate object models. An important design decision was the choice of programming language. Based on the past favorable experience, we decided to use in-house object-oriented programming language called DSM. So DSM's class library provided us with several convenient choice for handling associations. The DSM can implement associations with foreign keys, set, arrays, tables, and built-in generic association type. Our choice of technique was determined by the type of access required. We frequently used foreign keys and arrays. For example, a polygon object may access points through the array points stored in the points attribute. A point object may access polygon through a parent attribute. Since point may belong to exactly one of several different types of objects, the data type of parent is object. Object indicates that the value of an object but does not specify the class. The internal meta model captures the intended meaning of object diagram. Initially, this model was similar to previous figure. However, much of the internal meta model was needed to implement, so we simplified it during design. In the end, the internal meta model was simple mapping of blocks and nets into the classes and relationships. So each class have attribute as well as block. So each class have properties such as object, class name, database table name, and primary key name. Then there is a relationship name, database table name, and relationship with net. So we had converted the database meta model into database tables to the bootstrap system. The object diagram compiler was only intended to the compiler bill of material diagram, and thus it cannot itself compile itself. Then third, connectivity algorithm. A commonly occurring theme in the object diagram compiler is determining connections. Lines connect to the rectangles, ellipse, and each other. Text is contained in rectangles and adjacent to the lines. Rectangles are adjacent to each other. During design, we observed that each of these separate problems could be reduced to a special case of more general problem. Find the intersection of bounding box with bag of points. For each page and element type, we construct bag of points as follows. A bag is the same as a mathematical set, except it may have duplicates. So for each rectangle, we add 4 corner points to the rectangle bag, and each corner point is an object that contains a pointer to its parent rectangle. Each line adds new point object to the line bag. A line of text adds one point object to the text bag, and similarly for other graphical primitives. Then for for example, we find all rectangle inserting a line by constructing a bounding box around the line and checking the intersection of bounding box with rectangle bag of points. We have used a a doubly sorted dictionary to efficiently searching a bag of points for intersections with bounding box, and each bag of point is first sorted on the x coordinator and then sorted on y coordinator. So this figure shows object model for our point. So each page, that is element type, have a bag of x coordinator, then strip of y, then x coordinator and y coordinator, then there is a title with the coordinates x and y. This is the access structure or graphical primitive. So to insert a point, first the strip to which the point belongs, try for the exact match of the x coordinate in the qualified association between bag and strip. If none is found, create a new strip and add associations. Next, find the title to which the point belongs by trying for exact match on the y coordinator in the qualified association between strip and tile. If none is found, create a new tile. Finally, associate the point with the tile. The tiles are not uniform size. Figure shows the 12 points. There are 12 points. These 4 points, these 4 points, and these 4 points. 7 strips. There are total 7 strips. This is first strip, second strip, third strip, fourth strip, fifth, sixth, and seventh strips. So each tile has a point at the lower left hand corner. Each tile have lower left corner. When points coincide, one tile corresponds to multiple points. A tile is merely useful abstraction for organizing points in a search space for efficient intervals searches. So deletion is similar except tiles and strips are deleted as they become empty. So searching starts with the x values of bounding box. We implemented a special operation on the qualified association that returns all strips between the minimum and maximum values. Then we queried the y qualified association to determine all the tiles in the strip between y values of bounding box. Finally, all points associated with tiles were added to the collection of points found. We convert the collection of points into set of graphical primitives by traversing the association between point and graphical primitive. So we had several reasons for constructing a general purpose connectivity routine. First of all, we expected that finding connections would be common operation and we wanted efficiency. The naive algorithm of checking all possible combinations of element on page yields on execution time proportional to the square of number of elements. In contrast, our algorithm is linear with number of elements and connections. Our problems have a limited number of connections. So in practice, the order of the execution time was effectively reduced from n square to n, where n is a number of elements. Our algorithm has the disadvantage of added complexity. Thus, we wanted to design a general purpose routine once and reuse it for all special cases. Line intersect line intersect line intersect line, line intersect rectangle, and so forth. Then next part is implementation. We implemented object diagram compiler with DSM language. DSM is house in-house object oriented programming language that is implemented on the top of C. The first code was 13,000 lines long of DSM language. It took one person 3 months to develop a diagram compiler. 6 weeks were consumed by analysis and design, and 6 weeks by coding and debugging. About 20 bugs were found for developing this DSM language by using the C compiler. The compiler is presently being used for several bill of material generation applications. One application has a current input of more than 100 classes and 150 association yielding a graphics editor file with over 30 13,000 lines. The compiler run fast, compiling 5,000 lines per minute. This was the pleasant surprise because we initially feared that using object-oriented languages might degrade performance. The object diagram compiler fully satisfied its requirement. Our success with the compiler has motivated work on more comprehensive software to support OMT methodology. So, with what we have studied in today's lecture, we draw the following conclusions for our experience in developing object diagram compiler. Stick the object association paradigms and avoid temptation using stack, pointer and other data structures. In most cases, the use of association eliminates the need for the complex data structures. The use of limited number of paradigms and rich library container classes greatly cut the number of bugs and increased our software development productivity. When making enhancement, do not just patch the design, rethink and analysis. Whenever we violate these rules, we wasted time and made errors. Think through the consequence enhancement deeply and not superficially. Batch software is much easier to write than interactive software. Batch software does not need to contend with user interface and dialogue consideration. Next part is computer animation. So in computer animation, we will study what is the background of computer animation, what is the problem statement, analysis, system design. Okay, so first we will see what is a computer animation. Computer animation system creates sequence of images which when show one after another create illusion of motion. For example, Motu Patlu, Chota Bheem, etc. So computer animation systems requires an extensible design so that new applications and new graphics hardware can be easily added. This part describes a three-dimensional computer animation system and the system is OSCAR, that is Object Oriented Scene Animator. Object Oriented Scene Animator, that is OSCAR, produces high quality film and video sequencing, the result of scientific and engineering calculations and experiments. The OSCAR automates the creation, control and management of 3D computer generated animation sequences. Using an object-oriented script language as its user interface, Oscar controls analysis, modeling, rendering, display, and filming. So, interfaces have been developed for scientific analysis programs in the areas of modular modeling, robotics, mechanisms, analysis, and fluid mechanics. The object oriented design has produced a system that lends itself to interfacing with existing and future applications. The Oscar application demonstrates how an object oriented design can be successfully implemented with non object oriented language. Oscar is written in C using object-oriented development environment that includes macros, runtime support for inheritance and instancing and message passing. Oscar includes an interpreter that permits user to create instances from the animation classes in the system and to control these instances by sending message. So Oscar is the result of research started in 1984 on the application of object oriented technology to industrial applications. Because we expected computer graphics systems to increase performance dramatically throughout the 1980s. We proposed developing a 3D computer graphics animation system that would allow scientists and engineers to study the results of the experiments and the analyze. At that time, no C-based object-oriented systems were generally available. So we developed our own object-oriented interpreter to support animation research. And this interpreter is called LYMB, which includes the runtime library and creating objects and communicating with them using commands and runtime message passing. The interpreter has no dependencies on computer animation. Animation knowledge is held with the animation specific classes. So the animation process, the Oscar simulates the steps in the traditional manual animation process. As in all disciplines, animation has its own terminology. We briefly describe the animation process, defining enough jargon for the reader to understand the Oscar system. The user of computer animation system acts as the producer, writer, director of the final animation sequence. This sequence may be played back on computer graphics terminal or recorded onto movie film or videotape. The producer manages the overall film production, keeping schedules, assigning tasks, and organizing resources. The writer creates scripts based on the requirements of the customer. The director controls the animation, positioning, the props, actors, cameras, and lights. So the animation process proceeds the following. First is story. The writer working with the customer develops a narrative story that describe the actors and their roles, including their appearance, dialogues, and actions. Writing an artist's process is difficult to assist with the computer, and the actors may include inanimate objects. Then storyboard. A storyboard is a graphic synopsis of the animation illustrating the appearance of the animation and the flow of the story. The storyboard contains a representative drawing for each major point in the story. The art director normally produces the storyboard. Then third part is script. The script contains the detailed positioning and the movement of the actors, cameras, and lighting in the animation. Some computer animation systems provide scripting languages. Since the script may change over the course of production, a good language allows the script to be easily modified when minor animation changes are required. Then fourth part is simulation. Experiments and simulations often provide the motion of the animation for scientific applications. Scientists and engineers are familiar with the application domain setup and execute these simulations. Simulations can be computation intensive. Fifth is models. Each props and actors in the animation must have a geometric model that describes its appearance. The model is translated during rendering process from the mathematical description into the portion of the 2D image. And last is preview. Before committing the animation sequence to film, a fast preview of the animation helps establish critical timing and the overall look of the final product, producing high quality film output is usually costly, so changes to the simulation should be made as early as possible. Next point is render. Rendering produces shared images for later display by applying algorithms to the geometric model, surface properties and lighting. The render operation corresponds to the assembling a single frame of conventional animation, rendering realistic effects such as multiple light resources, textures, shadow, translu- translucency, refraction can be computation intensive. The next part is recording. After rendering, images are recorded on either film or video, one frame at a time. A typical animation application is a three-dimensional molecular modeling. First, a batch simulation is run on supercomputer to compute the position of each atom in a vibrating molecule over a period of time. The actors are the atoms in the molecules and there are chemical bonds. The animator prepares a script viewing the module from interesting angles. A rapid previewing is essential because it is too hard to select the right viewing angles without seeing the results. The final animation is run at full resolution and a film is produced, actually exposing exposing a film of several minutes duration can take a full day of computer time. Then what is a problem statement in case of animation? A goal of graphics animation system is to provide automated system for the efficient creation, control and management of 3D computer generated animation sequence. The system provides facilities to record animation sequence of 16 mm film or video. The system also provides interfaces between diverse simulation, modeling and rendering systems. Realizing that the application of computer animation is broad, the system must adapt to new applications with minimal amount of new software. So following requirements delivered from the knowledge of conventional movie making process and the scientific and engineering analysis process. The movie animation metaphor used for that of stop frame animation. A stop frame animation system frames are recorded one at a time. All participants in the animations are changed slightly and another frame is exposed. The user input consists of text files that contain animation script. Scripts can be a reference, a library of complex actions, as well as a define new actions. The script language serves as a base for animation, descriptive and documentation of the animation. So each animation consists of one or more scenes. Within a given scene, the script can control any participant in the animation, including actors, cameras, and lights. Control is provided through list of actions that the director groups into the queues. Queues are active for user specified duration and specified actions applied to the object in the animation. Any valid statement in the animation language can be action. For example, an actor might be told to move at constant velocity during the scene. Each scene specifies the renderer that produces its frame images. So actors are active participants in the animation. They have shape, position, orientation, and appearance properties such as color and texture. For example, in a planetary exploration animation, actors would include planets, rings, satellites, rockets, stars, and the sun. The specification of actor motion must be flexible enough to allow rotations and scaling about arbitrary axes and origins. The visibility of individual actors must also be controllable. Often, it is useful to group actors together, so the system must provide a mechanism to allow actors to be collected and controlled all together. So, geometry of an actor is kept in geometric model. The models range from rigid motions of simple geometric shapes to complicated deformations of complex objects. Since modeling is a complicated and tedious task, the system must be able to use models that already exist. Also, users may have invested large amounts of training in the use of specific modelers. Modelers should quickly produce low resolution models during the previewing so that the computation time to produce high resolution model is only be required to detail the film. So all animation is viewed through a camera. Multiple cameras can exist, but only one active in a scene at a time. The user can place the camera in the environment and controls its aim and orientation. Different cameras movement Effects like panning, zooming, tracking are required. Multiple lights can be used to illuminate the animation. Lights can be turned on or off and their intensity can be controlled. Lights also have geometry, spherical, cylindrical, point or flood. Engineers and scientists who use system will rely on their own analysis programs to provide much of the physics of the animation. Therefore, and the animation system must provide a way to interface to these external programs, and these programs should not be modified just to interface with the animation system. So the interface burden must be borne by the animation system. The system must provide facility to track completion of frames and where they reside. The frame is one image in an animation sequence.
हो सर.
A frame,
भास्कर का किती वाजले की?
1 minute. A frame can be built from one rendered frame or a combination of rendered frames. A post production capability allows the user to recall frames, combine them with other frames, and manipulate them on a receding device. It is a too time consuming to specify incremental motion of each actor in an animation for each frame. So the system must provide the way to move objects along easily specified paths. Keyframing Keyframing is an animation technique that lets an animator specify complex motion by giving a few keyframes and letting a junior animator film in the intervening frames. A computerized animation system should have a keyframing capability in which the system interpolates the animation. So next part we will study in next lecture. We stop here.